Okay, we're back up and running. Um, Quiet here, but do you have any questions? You working on like project 5? Yeah. I know last time on Wednesday we were taking a look at this last project. What? I don't. Yeah, that seems new, right? Like, did they just put these up, or they must have? Yeah, it's fun. I feel like they should have put them on the next, like one more back, right? So that you can see from the back, right? Oh, maybe that one faces the other way. That would make more sense. But there's a camera mounted on it. Anyway. So last time we looked at like modeling the shape of the guitar neck when we have like a torque applied right at the end of the guitar. And what we find is that like using finite difference is an exact solution in this case. Like it ends up being a quadratic equation, and we can approximate a quadratic equation exactly with this fourth order finite difference method. Always nice when something like that works out. So then the next part is trying to figure out like natural frequencies and looking at the mode shapes. So we can go back into the readings, and it's the same kind of setup as in the reading. We look at finding natural frequencies of just one guitar, of one string. So 4.5 gram per meter with tension 88 newtons. So let's take a look at how this gets set up. So this is just 2 mass, 2 spring. We're going to come back to this guitar string. And the main thing that we're trying to do is figure out the eigenvalues of this matrix, like T over mu times that H squared. So in this case, when that K value, so T over dx squared times over that mu, with 6 nodes, we end up with that first natural frequency of 108. And yeah, do we want to look at mode shapes to start? Yeah, come back up. Let's just grab this part. And I don't like to print inside of a function. So we're going to get rid of that one. Yep, we don't need dx defined again. And let's see, do we have L, T, and mu are all defined? That looks good. I'm just grabbing some stuff so that rather than return like the eigenvalues themselves, I'm going to return like frequencies. So just converting those radians per second into, well, really it's like radians per second squared because it's omega squared, but convert that into our natural frequencies. So each eigenvector is going to have some frequency associated with it. Oh, and let's get rid of that one. So if I look at guitar modes with 6, it would help if I'm actually importing the stuff that I need. Let's see. So I get these different natural with 6, with a 6x6 kind of A matrix. Then there has to be 6 eigenvalues, which means we can solve for as many as 6 natural frequencies. So 194, 380, 544. And let's double check that if we have so if I take the same results from if I look at the same guitar string that we were looking at in the reading, I can generate the same natural frequencies that I was getting when I first did the reading. And then this second array is it's a 6x6 eigen. So it spits it out as an eigenvector array, but really it's like one vector per frequency. So mode 1, the mode shape is this first column, and mode 2, the mode shape is the second column. So when I look at like column 0, it's half of a sine wave. And if I look at column 2, or column 1, it's a full piece of a sine wave. Like I still need the boundary conditions in there, but and the more points that I have, the smoother that mode shape is going to look, because we're solving for like in that vibration mode, how are all the nodes kind of connected if it's vibrating only in that mode. So we want to figure out like how well these are converging, and the mode shape is one way that we can look at how well it converges is n comma f bracket 0. We could think like one way we could look at this is just thinking about like if all I care about is mode 1, let me keep increasing the number of nodes and see how much that mode 1 frequency changes. It would help if I had colon at the end. and we can see like it keeps getting closer to that 109 point something. So 6 was a little too small for that first mode, and 70 is probably more than enough. And probably let's do like a semi-log x. So we can kind of see anything in the 100-ish is more than enough to be converged. 50 to 100. We'll do blue squares and black circles. And then we can see like mode 1, mode 2, where those modes are as they're changing. Same thing, like by the time you get to 100, more than enough even for mode 2. So we should see the same kind of effect on the eigenvectors as well. So like on these mode shapes. Seven, 8. And here I'm doing a little bit of like fancy stuff, but defining my x coordinate for the mode shape, because the mode shape starts at 0, goes to length L, and so it takes dx steps, but we need an extra step on either side, one to go from 0 to node 1, and then another one to go from node n out to that last boundary condition. And then this function of pad is going to add a 0 on either end of my vector there. And if I can do it once, I can do it as many times as I want. Let's look at the same steps, right? Now it's starting, it looks good. Like it looks like it keeps getting smoother, like I'm getting a better and better half sine wave prediction here. But the magnitude keeps changing because eigenvectors there is no like prescribed magnitude for an eigenvector. So one way to deal with this is like divide by max of v0. Oh. should work, right? I'm just trying to get them all to go. Oh yeah, that's right. Because we keep flipping. All right, so let's go back to what we had before. So right now, max is going to pick out for that gray and the green line. It's going to pick it out and normalize it from 0 to 1. But then on the yellow and red line, it's going to pick out the end points and divide by those, like over here. So we need this one. We can do like absolute value because we don't care if everything is just a positive number. But then the next one will be a little trickier. And see how some are flipped upside down, others are right side up. So we can look at absolute value there, and then they all kind of line up. They just keep getting a better and better approximation for that mode shape. But then when I try to do mode 2, just taking same code, trying it again, it looks a little weird because I'm taking absolute value of it. So I don't want to do absolute value. But sometimes it is flipped. So how did we fix this? How could we fix this? Like we could split it up into left and right half or something. It does the scaling works pretty well because there's a max and a min that are equal to each other. But I want to flip some of them. So if v1 comma 1 is less than 0, I'm going to try that and say like if this first node is less than 0, so like if it's going down, I'm going to multiply the whole eigenvector by -1, and just so that everything is always starting off as a positive slope. Let's see how that one works. There we go. Looks pretty good. We'll catch up. So just using some of our like derivative knowledge there. And then for, I think we want to do like mode 3, right? First 3 modes, yeah. So we'll do one more. But now I want to look at 2 Look at column 2. Look at that. Looking pretty good. All keeps getting closer and closer to that sine wave that we would expect, or like 1.5 sine waves that we would expect for a vibrating string like that. Trying to scroll down some. So now I have some different string values for like density and tension. And I could run through each of those. Yeah. So all the lengths are the same. Tension is going to be string val 1, and density is going to be and then I'm going to grab that stuff that I was just working on. You know what? Let's just grab this one. Oh, 0, 1. Sorry about that. 0, or sorry, this should be 1 and 0. Oh, and then we got to plot 0, 1, and 2. And I went through like all of these I went through all 6 strings, but all of them, as I change those tensions and densities, it's all like same vibration modes. It's nothing's changing. At least if I scale them all to put them all on the same scale. We can try changing, we could try like getting rid of that normalizing part. It's probably going to be busy. Oh, yeah, it doesn't really change, right? So it's just showing us that those three mode shapes are the same for any string as we're changing those k values. No difference. Or if I look at like output of what frequencies those are all vibrating at, have like 105, 78, 62, 46, 35, 26, 105. Is that right? E? Is E higher? 1, 2, 3, 4, 5, 6. Oh yeah. Okay. So every string is a little bit lower frequency, a lower note than the last string. That's right. 105, 78, 62. There's only there are more than 3 curves. It's just they all look like the same curve. Yeah. And that's what we should be getting, because the string, it doesn't really matter what note it's playing. It's just these are the vibration modes of that string as it plays. And if we're not changing like how many nodes that we were using, so here it's that whatever the last one was, so like 100 nodes, they're all going to look exactly the same. Yeah. And that's scaling or not scaling. All right, so can we listen to this? Let's save those frequencies. String notes. We want 6 strings and 3 notes each. This is just how, so in this is just how I'm thinking about it. Like I can enumerate this thing. That way I have, like, instead of just printing out those numbers and trying to reuse them, now I've got an array full of each of those frequencies that I want to listen to. And here, if I want, I could flatten it all and just make it a one-dimensional array, or I can leave it this way. Yeah. And here I'm kind of going through each note and adding a sine wave to it of each of those. This is all I care about, like in this analysis, just finding what are those natural frequencies. I'm not trying to figure, and the mode shapes, I want to know what they are and make sure that they look the way that they should. But then I can loop through, add all those sine waves together. Let's take a look at T and our signal. Looks pretty noisy. Something's happening. And it helps to zoom in a little bit to see. Let's go to like so if we just look at the first 100 milliseconds of what we're going to listen to, this is like all 6 strings vibrating in 3 modes each. That's a combination of all those sine waves. I didn't hear it. I'm going to multiply mine by 10. We're getting a noise. It's a little low for the it sounds pretty good. Sounds like a guitar that has been strummed but as played by a computer. But in terms of like creating a signal to listen to, we're trying to get natural frequencies, like so all the F1, 2, and 3 for each string based on its density, length, and tension. They all have the same length, different tension, different density to change how high or low the guitar string sound is. And yeah, then we can listen to it, we can look at it, we can do all sorts of stuff. And the listening to data like this, your ear is actually really good at picking up on small change. Like it's almost your ear is a Fourier transform mechanism, like your inner cochlea. It vibrates at different frequencies. So if there were some astrophysicists that were listening to interstellar data, like convert this kind of time series data, or even like X, like if kind of scanning along a theta direction, then convert that into an audio signal, and your ear can actually pick up like repeating signals and changes in the data pretty well. I was just thinking about, as you strum a guitar, there's a slight delay in each of the things. So we're going 0 to 3 seconds. Let's say delay 0 is 0, and then we've got 0.5 seconds, 0. And we'll go 0.75 to 255, 0.75, 1, 2, 3, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. I don't hear much of a change by adding that delay. Can you hear it? Yeah. I was trying to simulate like strumming the guitar. Yeah. Adding that phase change. Or I guess it's T minus that, right? Oh, that's why. Because it should be like times that Heaviside function, right? Like that. Now our signal looks different. So now we should be able to hear a difference. Definitely like clicking or something as we keep adding things to it. Cool. We've made it through project 5. Doing some mode shape stuff, looking at different notes. Anything else? Last 10 minutes of the semester, really.
derivatives. Just like the second derivatives, where your forward, central, and backwards are all the same function. Because when you take second derivatives, they're all the same function.
Yeah.
It's only when you plot it do you actually get different starting points, basically, ending points. Yeah. Does that follow for? I don't think it does for there because you're changing coefficients.
Yeah. The derivative coefficients change. I think the forward backwards times 2.
Times 3.
Oh, sorry. Times
3 times 2.
Times 2 for the central.
But it's the same concept in terms of indexing. Right?
Yeah.
Because you're going +2 minus 2.
Yeah.
So you have to start at the second index. For central difference. You're going to go
For central, we start, yeah.
the second index because you're going to go backwards too.
Yeah, to get 1 and 0.
Yes. Okay.
Yeah.
Yeah, taking a look, coming back to like derivatives. Yeah, with these like forward and backward third, the second derivative is a little. It's kind of weird because it's the exact same equation whether it's forward, backward, or central. It just changes where it gets evaluated. But and then in general, the forward and backward equation is always the same like values that you're subtracting from each other.
Plotting it is where you're starting.
Exactly. Yeah. But then central is, I want to say, I think the even, so it's like second, fourth, sixth, eighth. I think the even numbers are the same equations as forward, backward, and then the odd ones have a different equation.
Gotcha.
And I'm trying to remember if that is always true. There's not too many times where you end up with like a 10th derivative equation. Usually fourth order derivatives is about as high as boundary value problems get, like Euler-Bernoulli and plate theory, Kirchhoff bending. Yeah, and like if you're taking the fourth derivative of a function, you need 5 data points. So you need your current value and 4 others either. So if it's central difference, then you need 2 in front, 2 behind. And if it's forward difference, you need 4 in front of it. Backward is 4 behind it. Because most of these derivatives are all approximate, saying like, okay, these data points are a polynomial, and I'm going to take derivatives of that polynomial until I get a constant value. Yep. term. Yep. Yep. Okay. Yeah, so this one, when you end up with W1, so we need W2 and W3, but we also need 0, which is 0. So anytime 0, this is 0. Then we also need negative 1. The negative 1 equals W1 because the slope is 0 at 0. Because slope is 0 at 0, but that fictional negative 1 would have to be equal to so like, so the idea is like we have 3 points all sitting on a line, and I know that the middle of the line from W0 is 0, so then I can move W1. If I move W1 up, then negative 1 goes down. I put it down, goes up. And then I have another boundary condition of slope is 0. So that straight line is slope is 0. So okay. Equal to each other. Negative. So we have positive W1 and W0 cancel out. Yeah. Yeah, so we have like a W negative 1 plus 6 W1. But that negative 1 is W1, so I have 6 goes to 7. Yep. Thanks. Oh, nice. Oh, with no speaker. Yeah. So maybe yeah. Okay. So I know, yeah. It's more like the way we're using. Yeah. Thanks a lot. You too? Thanks a lot. There you go. Yeah. Cool. Very nice. Thanks so much. It's been a pleasure. See you next year.